Okay, uh, projectile motion refers to the motion of an object that is launched into the air and moves under the influence of gravity, following a curved trajectory. It can be analyzed as a combination of two types. The horizontal motion, this is a uniform motion where the object moves at a constant velocity, at a constant horizontal velocity. There are no forces acting on the object in the horizontal direction, assuming air resistance is negligible. Vertical motion, this is uniformly accelerated motion due to gravity, where the object accelerates downward at approximately 9.81 meter per second squared on Earth. So we have the key characteristics. Trajectory, the path followed by the projectile is typically a parabola. Initial velocity, the angle and speed at which the object is launched affect its range and maximum height. Time of flight, the total time the projectile remains in the air. Range, the horizontal distance covered by the object. So we have the equation here for the motion of projectile motion. Can be derived from the basic kinematic equation. Some common equations include the horizontal range. So this is the square of the initial velocity times sine of the twice of the angle over g. So where r is the range and v sub 0 is the initial velocity, uh, angle theta is the launch angle, and g is the acceleration due to gravity. So we have also the maximum height. Okay, so later on, I will derive this. No? So this equation help predict the motion of the projectile under ideal conditions. The projectile is drawn upward with an initial velocity of 45 meters per second at an angle of 70 degrees with respect to the horizontal ground. All right, so the problems are find the magnitude and directions of position vector at time 3.5 seconds. So this refers to the time interval. Velocity at the time equal to 2.5 seconds. Find the x and y components of velocity at the highest point, maximum height, total time in air, and range r. So we have the solution for that. So the first problem is find the magnitude and direction of the position vector at time 3.5 seconds. So the x and y displacement are given with this formula. No? Uh, x component of the initial velocity times the time for the x displacement. For the y displacement, we have initial velocity of the y component multiplied by time minus 1 half gt squared. The magnitude of the position vector r is given by this, given by the uh, Pythagorean theorem, the square root of the x squared plus y squared, and the direction of the angle is given by this term. So substitute 3.5 in the equation by Mathematica programming. We have the initial x component of the initial velocity, the y component of the initial velocity. The time is equal to 3.5. Now we have the acceleration due to gravity here, 9.8. And we have the x displacement, x component of velocity times the time. So we have to use the print and so we have, here's this formula. No? So the formula to be used is the y component of the initial velocity multiplied by line minus 1 half gt squared. So we have the acceleration due to gravity. And we have to find the value of y, no? By using the command print, we have the square root of x squared and y squared. Okay, so uh, if we enter this, so we have the values of x, x displacement is equal to 53.86 and y equal to 87.97. So using the Pythagorean theorem, uh, the magnitude of the position vector is 103.158 meters. the corresponding direction of the position vector is 50.52 degrees. So the angle here is in terms of the degree. So as what I have written here, no, it is expressed in degree. Okay. Problem number two is so what is the problem number two here? So find the velocity at time uh, after the interval of 2.5 seconds. Okay. So the x component of the initial velocity are the same, no? The initial the it, the x component of the initial velocity is equal to the x component of the final velocity. So that is 45 times cosine 70 degrees. The y component of the initial velocities are so this is the y components of the initial and so and final velocity are respectively 45 meter per second times 970 degrees. So this is the y component of the initial velocity. The the y component of the final velocity is given by this one. Okay, so and the direction is given by this. But the y component of the initial velocity is the y component of the initial velocity is given by this vy sub 0, 45 sin 45 times sine 70 degrees. And the direction is the arc tangent of the y component velocity over the x component of the uh, velocity. So mathematical programming is given by, so we have this, clear natin yung, let's first clear the Vy sub 0. So we have here the x component of the initial velocity. Yeah, so that's constant because the x component of the initial velocity is equal to the x component of the final velocity. But the y component of the initial velocity is not constant, no? Because of the effect of the acceleration due to gravity. All right, so here, no? So this is our mathematical programming. So if we enter this one, so our velocity is 23 point meter per second. This, in terms of meter per second. And the direction of the velocity is so in terms this is in terms of degree. Okay. Okay. So question number 3 is what are the x and y components of velocity at the highest point? So the x component of the velocity at the highest point is constant throughout the flight. So the so this is wrong. So it should be so the x component is 45 cosine 70 degrees, and the y component is the y component velocity at the highest point is equal to 0. Yeah. Because if the y component of the velocity at the highest point is not equal to 0, that the projectile will continue to move. Okay. All right. So question number 4 or problem number 4. What is the maximum height? So find the maximum height, no? So maximum height occurs at final velocity, no? So if the y component of the final velocity is equal to 0, So that is the location, no? So that is where the uh, maximum height, no? So the maximum height is a point, no, where the final velocity is the y component of the final velocity is equal to 0. So we have to use this equation. Okay. So we have this is our program for the y com this is our program for the equation. So let us make a code for this, no, using the Mathematica. So our answer here is 91.23.06. So this is also in terms of uh, meter, no? Okay. So the next question is find the total time in the air, no? So we have the y. So the final velocity of the y component of the final velocity is given by this equations. So at the highest point, the y component of the final velocity is equal to 0. The projectile is at the highest point. Okay, so here, the y component of the final velocity is equal to 0. So this is the y component of the initial velocity. Now acceleration to gravity is 9.8. No? So using this formula, all right, this. So we have the formula here. So this formula uh, is the same as this. No? So, okay, so we have the result here. No? So the time at the highest point is 4.31 seconds. So uh, this is in terms of seconds. Okay. So the next problem is find the range, no? At so after the total time. So the range is equal to the x component velocity times the total time. So time at the highest point is 4.31. So the total time in the air is 2 times 4.31 seconds. So that is 8.62. So the solution is here. No? So we have the solutions. No? So the range in meter is 132.67 by Mathematica programming. Now we have the displacement here as a function of time, and we have the x displacement as a function of time. This one. So what we are going to do is uh, what we are going to do is to eliminate the time t, no, in this equation. We have the parametric equations. So these are the two parametric equations, and we are going to eliminate the t here, no. So solving for the time here and substitute in these equations, we have this. So we have here y in terms of x. Now we now plot y versus x. No? Okay. So we use this equation to plot y versus x. So what we have here is so this our it's my mathematical programming. Okay. So I show to you the code, no, that I made. So it's quite a long. No? And, the image size is 500, and the aspect ratio is equal to 1. So I made it a little larger to see the image. Okay, so our x here. So this is the range, no, 132.82 meters. And this one, this is the 87.97 is equal to, so this is the 87.97 meter. So this is the height of the projectile after a time of 3.5 seconds. And after a time of 3.7, the x component of the displacement uh, is equal to, uh, so we have the x component of so this one. So this is the x component of the position vector after a time of 3.5 seconds. Now this is the displacement of the uh, position vector after a time of 3.5 seconds. Now after a time at the highest point, that is the time at the highest point is I think 4.32. So this one. So after a time of after a time at the highest point, the maximum height is 91.23. So this is the equation. So 91.23. The height at the time equal to 3.5. So this one. Then we have the distance. This is the x component of the distance after 2.5 seconds, and this one. And this is the vertical component of the distance of the position vector after 2.5 seconds. Okay. But this one, uh, this uh, uh, this is the highest point. So after a time of 4.32 seconds, uh, the projectile is located at its highest point. So what is the time at the highest point? That is equal to 4.31. So this one. So this is the time at the highest point. So if we multiply that by 2, what we have is the total time. So 4.31 times 2 is equal to 8.62. And that is what we use in the finding the range. So we have here the range of 132.67. No? So that is equal to the product of the total time and the x component of velocity. So this position vector, actually the position vector here is only up to the intersection of the curve and this position vector. So we have here, so this is the position vector. So the position vector is up to only this point. So I compute for the height of this. So what is the height of this though? So this is 87.97. And so what is the corresponding length? The corresponding length is given by this, no? The corresponding length is given by 53.86. Uh, 53.86 is it, no? Now, actually, this is the slope form of the line, no? By using the slope form of the line, uh, we have 97, uh, 66, no? 87, 87, no? 0.9766 x over 53.86, 82. No? Right. So we have the maximum height here, height at the at after time at 3.5 seconds. Now the velocity after 2.5 seconds here, no? So after 2.5 seconds, we have the uh, we have the slope here, no? So the slope here is the y component of velocity with respect to the x component. So it is the velocity after a time of 2.5 seconds. Right, so that's all.